Ma'am, Uma Mageshwari ma'am.
Yes, sir. I am online.
Okay, ma'am. Okay, ma'am. Ma'am, another 2 minutes, ma'am. 2 o'clock.
Yes, sure.
Okay, ma'am. Ma'am, shall we start, ma'am? Ma'am, Uma Mageshwari ma'am.
Yes, sir. Shall we?
Okay, ma'am. Thank you, ma'am.
Yes.
Dear participants, welcome to Kongunadu College of Engineering and Technology. So, on behalf of Kongunadu College of Engineering and Technology, AICTE sponsored 2 weeks online faculty development program on emerging trends and challenges in VLSI mixed signal processing for fourth industrial revolution. Today, day 9 and session 2. Today, our resource person Mrs. Uma Maheshwari, Manager Technology, Pramura Software Private Limited, Coimbatore, Tamil Nadu. Welcoming, ma'am.
Yes, sir. Thank you
Thank you
your warm welcome, sir.
Thank you, ma'am. So before going to start the session, a small introduction about today our resource person. So I call upon Mr. Bhaskar introduce our resource person.
Good afternoon to everyone. This one afternoon, let me see the short intro about our resource person, Mrs. Uma Maheshwari. She completed her Bachelor of Engineering in Electrical and Electronics Engineering in Amrita Institute of Technology, Coimbatore, and completed her ME in Embedded System and Technologies in Anna University, and pursuing her part-time PhD in the area of EMI filter design. Her area of expertise includes a high-speed PCB design, post-processing of a PCB design, process improvement, cross-functional analysis, customer relationship. She published 10 technical articles in referred national and international journals, and also published a book in the title of Power Electronics with MATLAB, the Cambridge University Press, London, Simulation Tools for an Electrical System, writing book in the title Electrical Machines with MATLAB. She conducted a 1-credit course for a UG and PG students in the area of PCB design system and EMI mitigation method. She is a certified Japanese language proficiency test JLPT N3 certificate holder and conducted courses for students and industrial persons for Japanese language. She is one of a Japanese language translator for a technical documents and acted as a keynote speaker in various international and national workshops and conferences. In this way, now I'd like to hand over the session to our resource person, Mrs. Y. Uma Maheshwari, who is going to handle the session on the topic of PCB design demo in the EDA tool. Please, ma'am.
Thank you, sir, for your kind introduction. And first, let me share my screen. Hope my screen is visible.
Yes, ma'am, visible, ma'am.
Yes. So, a warm good afternoon to everyone who are all present here. So, this is Uma Maheshwari, and from now on, for 2 hours, I will be taking related to the PCB design, how the PCB design can be done in a EDA tool. So, after your VLSI or FPGA, whatever design circuit design, it will be definitely translated into a PCB. So for every project or every application you see, there will be a PCB sitting on it. So the design of PCB is very essential, and it is not a simple thing for in case of high speed PCB design, high speed signal operating conditions. So we need to pay attention each and every part of a PCB for the signal integrity and other noise and other mitigation techniques. For each and everything we need to take care in the PCB level itself. So for the circuit side, circuit design or VLSI design side, you will be doing some level of simulations and other activities, but those will not be sufficient when it comes to the PCB. So in the PCB also we need to pay attention in the EDA using the EDA tool and other simulation tools subsequently. So the PCB design actually is not in a part of a syllabus or part of a curriculum in the engineering stream. So just I would like to share my ideas or share my gist for the related to the PCB design, and after completing this 2-hour session, you will be having some idea about the designing of the PCB, and you can do a simple circuit. I mean, with simple PCB design out of the thing. So anyway, this is actually, in the 2 hours will not be enough, but I'll try to cover. I'll try to give the overall view of this PCB design domain. So I have two presentations, like only like first one is about the PCB design circuit. So just a basic fundamentals of this PCB design, and the second part is the PCB design flow, how the design flow could happen over the process, and subsequently I'll work out with the things in the EDA tool, that is electronic design automation tool, for doing the PCB design. So let me start this presentation, basic presentation initially. I'll just quickly go through the terms and terminologies which are involved in the PCB design. So this is the basic agenda of the presentation. So what is PCB? As we all know, the PCB is a thin board which you see in the every electronic equipment. The circuit is translated into the PCB. There is circuit diagram is laid out in the PCB, which is non-conductive material. So conductive portions alone is the copper, where the current or signal passes through between the components. So the signal path is called, in the PCB domain, is called tracks or traces. So normally, based on the temperature of the application, that is temperature withstanding capability, or based on the flexibility, or various reasons, we will select the board material, that is PCB board material. Could be the FR4 glass epoxy or the polyamide, or various types of materials are available. So common material is FR4 glass epoxy material. So what the material will play the role is, actually it acts as a dielectric between the copper layers. So the main parts of the component, PCBs are the components will be there, pads will be there, traces, vias, and layers. So these are all the major components, major parts, which consist of the PCB. So we'll just quickly go through those components, those parts of PCB. So we know the components as an electrical or electronics engineers. We definitely know the components. There are mainly two types of components are present. One is leaded components, and the other one is leadless components, that is surface mount components. So for the same capacity of the value, that is, for example, if you take 0.1 microfarad of capacitance, you'll be having the leaded capacitor component as well as the surface mount capacitor. So compared to the real estate part, that is the volume of the component, that is the space which occupied by the component, is very less in case of surface mount component, and it has some other advantages also. In case of the high speed frequency board applications, the surface mount component will not have the lead inductance effect. So the lead inductance will leads to the impedance mismatch of the PCB. So that will again leads to the electromagnetic interference or other signal integrity issues. So in case of the high speed applications, PCB applications, we should definitely use the surface mount technology. So leaded part can be conventionally used in case of lower frequency applications. So as we saw, the advantage, we don't need to drill the board, so that the rigidity of the board can be maintained. And in the case of through-hole components, it is leaded component, we need to drill the board and we have to solder it properly. So these are all the various packages available in case of the components, whether it is leaded or leadless. There are many types of packages. So based on the applications or circuit, we can choose the component according to the part numbers. And types of vias we have, there are 3-4 types of vias are available. So one is via is nothing but the hole which can be drilled in on the PCB. So the via from the top to bottom via, if we drill the via hole, that is called the through hole via. So through hole via has the connectivity from the top to bottom layer. And in case of blind vias, partial connectivity can be established. That is from the top to the inner side of the PCB, and from bottom to the inner side of the PCB. So the blind via here is connected between the top and the next immediate layer of the PCB. Similarly, this is also a blind via. And buried via is in the case of connectivity between the layers, which is exclusive of the top and bottom layer. And some of the high-end PCBs involves micro vias, which is very less hole size, which has many advantages in case of signal integrity as well as the board size. So in high-end applications such as mobile phone applications or radar or other applications involves the micro vias, which is around 150 to 60 micron is of the diameter. So also that has the more realistic, so that the complexity of the board can be increased because of this advantages. The second part is the pads. So pads is actually a copper pattern where the components can be connected to the or soldered to the board. So you just imagine the it is a copper pattern which has the round in shape or rectangle in shape or square in shape based on your lead or leadless component values. So just pads are the copper pattern which can be used for the component to solder in the PCB. So the next part is the trace. The traces are, as we discussed, these are copper wires. In case of wire, we can call external wires, or can be you can imagine the compared with the external wires. So this is traces are nothing but the copper wires, which is laid out on the PCB. So this is the conductive part, and we can call it as a tracks or traces. And based on the current carrying capacity of the signal, that is based on the current, we can choose the trace width, that is cross section. And in case of signals, it may be a narrower, and in case of power, and if you want to route the make the connections for power and ground signals, power and ground traces, we have to have the wider trace width. And the process of doing these traces is called routing. So routing is a process. Okay. And there are some other techniques we need to follow while tracing the tracks. So we need to maintain certain distance to avoid the short or the crosstalk in between the signals. And in case of the neck down, see the below picture shows that we need to take the trace from in between these two pads. So in such case, we can neck down the trace, and immediately after this, if you have the space, it can be in the regular trace width. So initially, what in the EDA tool does is we need to place the components and making the connections. This rubber band line shows the connectivity between the components. So you can see the green signal. So this is actually starting from here and goes to here, this component, and again it goes to this component, and from here it is going to this one. So the whole part is called the signal. That is a one signal, which is also called net. So this net, that is this rubber band lines, will assist us to draw the or to connect the components between the components. So this is very essential in the case of routing process. So I will show in the demo how this can be established in the tool. So we need to make the clear routing like this in the left hand side, and the right hand side is a poor routing, which leads to the poor signaling part. And some of the terms we need to know before getting into this design. So this is, as we know, this is a trace. This is a trace actually. So based on the current which you are going to send, that can be trace width can be decided, and there are some other calculations are available for determining the trace width. And we need to maintain certain distance, that is that terminology is called track to track distance. So similarly for pad, we need to have pad. This is actually a pad where we are going to drill, and the components can be placed using inside the drill. I mean inside this hole. So this is pad. So this is a copper pattern. This is another copper pattern on which the center of the pad is drilled to some particular hole size. So this is the hole size or drill size. This is the size which in here it is drilled, and the distance between pad to pad should be maintained, and the whole copper size is called LAN size. So another terminology is vias. So vias we saw already. So this is nothing but this is also a pad. That is a copper pattern which is purely used for the connectivity purpose. So connectivity in the sense, if your design is very complex enough, or you need to reduce the size of the board, we need to increase the number of layers such that we can reduce the board size. So from one layer to the another layer, the traces has to be translated into through this via. Picture of how the vias are transmitting the signal from one layer to another layer. So as of now, via is assumed as a pad which is used for the connecting the traces. So this is the cross section of the hole where this is the top surface of the top copper surface on which the pad is drilled. That is vias or pads are drilled, and here the walls of the copper, that is walls of the drill, are plated, so that we get the connect. If you probe the connectivity here, if you probe it here, you will get the connectivity through this. Yeah, this since this is a plated one. So another concept is layer. So layer, as we know, we have many types of PCBs like single layer PCB, double layer PCB, or multi-layer PCB. So in case of single layer PCB, you will have only one layer, that is one copper layer which is sitting on the FR4 board material. In the case of two layer PCB, there will be two layers, that is top layer and the bottom layer, and in between these two copper layer, there will be the board material like FR4 epoxy, glass epoxy. So similarly, if your circuit has a more complex component or more complex thing, and you need to reduce the board size, we definitely need to go for the multi-layer PCB. In that case, you can shrink the board size and you can increase the layer size. So if you increase the number of layers very well, but in the case of cost perspective, there will be definitely more process involved. So single layer board is very cheaper, and double layer board is very little expensive compared to the single layer board, and multi-layer board is very much expensive. So number of layer we need to it will be a very much trade-off between the cost and the board size and other applications, etc. So as much as possible, we need to minimize the vias and minimize the number of layers. So that will be the challenge of the PCB designer. And here, as you see, we have the top layer and the bottom layer and the internal layer. As internal layer, that can be a signal layer or power or ground layer. And above the top layer, we have the top mask layer, and which is used for purely masking purpose, that is protecting purpose. And similarly, the bottom, since it's a copper, it is easily oxidized with the humid present in the air. So it has to be coated and masked. And similarly, the bottom layer also it has to be masked, and that layer is called bottom mask layer. So the green color which you see normally in the PCB is a mask layer which is non-conductive in nature. And above the mask layer there will be a silk layer. That is, silk layer is actually a text layer which indicates a component designation and some other information like logos, company's logo, or the power supply or component designators. So this will be very, very helpful for in the case of assembling or the troubleshooting purpose. Similarly, and below the bottom mask layer there will be silk layer. So this I'll we discuss. So this green color represents this green, and red color represents the mask layer. So normally we use green layer, and this is some other purpose. So based on the properties we'll select the mask. Okay. Then so the white color text indicates the silk layer. See here the connector has the RST and 3-volt and ground pins. So if you don't have the silk layer, you will not get the clear position for probing or testing it or mounting a component. So solder mask layer I have discussed already. So this is this purpose of this mask layer is the protecting purpose. And board material we saw generally a glass epoxy material. So this is a non-conductive material. So what they will usually have is there is a concept of core. So the core has the board material over which the copper foils are laminated, and you can see here very well. And the center portion is actually what I indicate. The center portion is actually the PCB core, and the core upon the core, that is upon the top and bottom side of the core can be copper laminated material, copper material. And if you want if you want to design the 2-layer board, this copper core is enough for doing the design. And if you want to increase the number of layers, we'll add the pre-peg, which is also a non-conductive material, and upon which the copper layer is laminated. So this is how the number of layers are increased for the thing. So this is a typical cross section of the multi-layer PCB, where you can see this is a through hole where the holes are copper plated. Thereby you will get the connectivity. If you take the trace in this ground layer, you will get the connectivity. So this is a typical 8-layer board. 8-layer board stack up details are given here. So you can see that in between the core and core, upon the core and below the core, you will have the copper layer and pre-peg layer and the copper layer and pre-peg layer. So all the things are should be symmetrical. So otherwise there will be many other practical difficulties will be raised. So normally it will be the number of layers will be in even layer. So coming to this via connectivity concept. So as I said, I have shown here only the via portion, via copper portion alone. So you can see in the top layer you have the copper via copper pad, that is via, and you have the walls are plated, so the drills of the walls are plated so that you will get the whole connectivity. How if you want to take the traces from here, this via to this via, you can very well take in the first layer. So here the 4 4-layer cross sections are shown here, and from the first layer I am taking the trace here, and if I cannot cross this wire. I cannot cross the trace because of this trace. So what I should do is I have to go to the next layer, and in the next layer I can make the connection between these 2 vias. So this is how the vias are helpful for routing the vias or switching to the other layer of the PCB. So normally units to be used are imperial or metric units, that is English and metric units. in the case of Asian countries, they use metric, and European and US countries are using English units. So so here now normally in India we use the that is metric values. So this is the conversions given here. So most of the time the PCB will be in dimension metric in India. So there are definitely as many standards are available for each and individual thing. So IPC is a organization which defines complete reference, that is complete standards for each and individual uh, uh, part of the PCB area. So for example, if you take the mask, or if you take the pad, how to create a pad, or how the pad should be and pad size should be, and for everything there will be a standard. So that IPC defines all the standards. And the standards has 2-3 classes. So class 1, class 2, class 3. So based on the class 1 or class 2 or class 3, based on your product application, you will select the classes. For example, if your product is in the general electronic product, you can choose the class 1 where there is no cosmetic imperfections are important. And if you are designing a dedicated service electronic products, definitely you need to refer the class 2 of IPC standards, where for example, in case of communication equipment, instruments, military equipments, you need a perfect response. No cosmetic imperfections are allowed here. So in that case, you need to select the class 2 standard. And the class 3 is a very tightly scheduled standard, that is military, like military and other biomedical applications. Definitely you need to select the class 3 standard for high reliability of this electronic product. So as we saw, there are many types of boards: single-sided, double-sided, multi-sided, with via, without via, with core, without. So like depending upon your board complexity, you can select the number of boards. And other type of boards are rigid boards, flex boards, and rigid flex boards. So what you see here is a rigid board. That is, you cannot bend the board, but you can reduce the board size by increasing the number of layers or whatever conditions you may have. And in case this is a conventional board, and this is the flex board where you can bend the board. The difference between these two is the rigid and flex is that you can bend the board, and the material you use here is a polyamide and other polyester material for laying out this copper pattern. So here you can bend it nicely, dynamically or statically, depending upon your application. So that is why this is called as a flex board. And some of the flex applications are in the IoT applications and other connector applications. So instead of using the external connector, you just use the flex board as a connector to avoid the switching or other noises, connecting noise. So you can see, so these two boards are connected here. This is another type of board, rigid flex, combination of rigid and flex. So instead of using the connector, here the flex board is used for as a connector. So the design process is a little different among these three types. So with this basics of the PCB is over. Till now, if you have any doubts, I'll before going to the next presentation, I will clarify your doubts. Hope you are clear with the concept. So I'll proceed with the next thing. So this is actually, as I discussed, next process is the design flow. So if you understand the design flow, I will show you the demo after this design flow part, and it will be very easier for you to understand. So there are many media tools are available. For example, Cadence. These are all the high-end players: Cadence, Metagraphics, Altium, Zuken. So these are all the high-end EDA tool vendors, which which is very high cost tool, which has the more features for doing the PCB design and simulation. So normally what the design process is actually logic design, physical design, and analysis and verification. So in the logic as well as the physical design, you will have the analysis and verification then and there. So the logic design is the first to the circuit design, or FPGA integration, or FPGA programming, or variants and reuse. So various logical kind of things has to be designed in particularly by the particular person, and the same is translated to the physical design team, that is PCB layout, which involves PCB layout, component placement, interactive routing, auto routing, manufacturing, and the files preparations. After the preparations, after the prototype or actual board, we will have the signal integrity analysis and other simulations, electromagnetic simulations, and other analysis has to be done. So all these three are put together as a complete domain of this stream. So in the physical design part, you have you need to have you need to have an EDA tool, and in the EDA tool, most of the tools or EDA tools will work on the concepts like library, where all the components will be stored in the library. From the library, you can retrieve the component and place it in the EDA tool, and you can make the connections, and you will do the component placement, routing, and what subsequent process can be done. So in the library, it is very important to maintain a component, creating a component, or you can copy from other libraries as well. So before starting the design, you need to create a library initially, and those library has mainly two types of component creation. One is the logical component creation, and the second one is the physical component creation. The logical component creation represents only the logical connectivity purpose, and the physical component is actually a design. That is, the physical component symbol has to be created as per the data sheet which is released by the manufacturer, and those two, that is physical and the logical components, will be combined together, make a component. So there will be a three parts in the library stage. One stage is we need to create the logical component, and the second stage is we need to create the physical component, and the third stage is we need to combine those two, logical and physical, and making a single component for the tool to understand it. So like I said, the library concept is in the ECAD tool will be you need to create the schematic library, footprint library, and 3D model is optional. So if you want to have the if you have the 3D element of the 3D file of the particular component, you can integrate within that. So the main roles of the PCB are, it's not like just making the connections. We have to take care the main various aspects of the process. Like we need to take care of the floor planning, that is size and other informations, and we need to interface properly to take care of the speed of operations, and the power and the frequency, that is signal sides, and the electrical constraints side we need to take care, and integrity of the thing. So receiver has to receive the perfect signal. So that is a main objective of this thing. And if you combine with the product design, you will have to, again, you need to draw the technical drawing, EMI verifications, EMI regulations, conditions, and other high speed bus planning, and everything we need to take in. So all put together forms a PCB design. And design flow involves, we need to create a schematic capture first. After designing the circuit simulation part has to be done separately, and in the EDA tool we need to draw the schematic, and from the schematic we need to translate, that is the logical component we created, right? So that component is represented by the schematic capture, and this logical has to be translated to the actual board size component, and that is which is in the video tool. So these two has the individual editor. So schematic editor will be separately present in the video tool, and as well as the PCB layout tool editor will be placed in separately. So we need to use these two editors and to create the actual board files actually. So using those files, we can send to this manufacturers, this PCB production, and you'll get the actual board. So for sending the files to the manufacturers, we are will be using common files like .gerber files, which is .gbr files, which is a text file which has the information about the component location and the size. We don't need to send the actual layout file to the manufacturers, because those persons will not be having the all other EDA tool licenses. So universal format is a Gerber file format, which will be sending to the manufacturers for the PCB production. So we'll see one by one what is these three represents. Schematic capture. The schematic capture, which shows the graphical representation of an electrical circuit, which you want to intend to design. And here the logical symbol can be inserted from the logical library, which we have already created before doing this design. And these components can be connected through the wires for making the connectivity purpose. This connections is translated to the layout side. So so as we see here, this capacitor and this buffer, there is op-amp is connected between this wire. So from the pin 1 of this capacitor and the pin 8 of this op-amp, so we need to, the tool understands that it is actually a connected one. So this connectivity information is carried here to this layout. So through this intermediate netlist file, it is carried out to the layout editor. So here you can see the A1, the name is A1, and A1 consists of these 11th pin of J1 and 13th pin of U2 and etc. So this is the information which is passed to the layout editor. So this is the layout editor. Here we can use the grids concept, so that the aesthetic point of view, we can make this grid value little wider or little bigger to get this placement done. And so this most of the EDA tools will work on this grid concept. So you can so if you don't want to use this grid concept, you can switch it off the grid. So this is the thing, and the properties of the component will be extracted from the data sheet of the which is released by the manufacturers, which has the complete analysis, that is complete characteristics of this component will be present, and the physical dimensions also will be present in the data sheet. So using this data values, will create the library in the thing. So as a gist, we'll see component libraries of DesignSpark. DesignSpark is an open source EDA tool, which I prefer to use here in this demo version, which is equivalent to the high-end vendors, which is actually open source. You can download the DesignSpark very well, and you can use it for the educational purpose. And here the library editor, that is library, has the schematic editor and the PCB editor, which gets the component from the component library. So the component library consists of a schematic symbol, PCB symbol, as well as 3D part of the symbol. So means that we need to create this schematic symbol and the PCB symbol. These two has to be combined and to make a common component library. So that is what here it is shown here. So this is actually individual component. We need to, from the individual component, we need to we are inserted from the library, and the components are connected as per the circuit which is simulated already, which is workable already. And yeah, suppose some connections may be there be a same node, there will be many connections will be established, so that can be used this wire node concept. And the wires are connected to the port, and there will be, if your circuit is very huge enough, you can if you cannot draw this in the one single page, you can increase the page so that the connectivity can be established between the pages. And before you start the layout, till now you have drawn the schematic side, and before you start the layout, we need to look at the manufacturer's website of the component which you are going to use in the library, use in the PCB, and we need to analyze clearly the characteristics of this component so that we can use the correct hole size and the correct trace with correct clearances and board size. Board size information, of course, the customers will be providing, or we will be the product designers will be designing that, and the limitations of concerning the board and board shape, of course, and the required Gerber format, required file format, that is from the EDA tool. You need to export the file to manufacturers, right? So that will be a Gerber format, or whatever format which they ask, we have to prepare. So before doing this layout, we need to concentrate on those parameters. And this is the typical design flow chart, which is for the doing the PCB design. So first we need to draw the schematic. After that, in the layout editor, we have to set up some environmental variable, and we need to input the netlist from the schematic, and we need to place the component. We need to make the routing, that is making the connections between the components as per the schematic circuit, and post-processing of the design, and finally the Gerber view and export the Gerber. So this is the typical flow of the design process. So quickly we see. So as we discussed, the actual footprint has to be created in the library, and this library we already created the symbol and the logical representation and the physical representation. These two are combined together and to make one component. Like so here we have the this NAND2, and this is actually DIP14. So these two are combined to form this component for easy placement in the respective editors. So after importing the netlist, step 2, after importing the netlist from the schematic editor. So in the schematic, we have made the wires between the components, right? So that establishes the connection between the components in the case of layer editor 2. And so these rubber band lines are shown here is the connectivity between the components, which is drawn in the schematic editor. So this is the information which carries from the schematic editor. So next is the so here the placements are actually, see, this is the board outline. So this is the board outline that is shown here. So the out of the board outline, the components are placed automatically from the library. So we need to arrange the board components inside the board outline. So the board outline is fixed based on even requirement or the client's requirement. So we cannot change the board outline, board size. This board outline represents the board size. Then the components has to be placed inside the board outline, and for the component placement also we need to have the clear things. So based on your frequency of applications and the signal operations, like analog, there may be a digital, so mixed signals, there will be RF signals. So those RF signals cannot be routed near to the analog signal. So like that. So there are many considerations has to be done while placing the components. And another kind of thing like connectors and other switches has to be placed very peripheral to the board outline for the easy access. So so each and every placement of a component has to be taken care. Similarly, for the placement of the decoupling capacitors near the IC, it has to be very proximity to the IC to address the power issues. So we cannot place away from the thing, so then it will not solve the purpose. And step 4 is the placing the ground and power distribution. So there may be a various powers which can be used in the single PCB. For example, there are 3.3 volt and 1.8 volt and 3.3 volt analog and like various powers will be there. So according to the power requirement, we can split the power in the power plane layer. So what I mean is we can share the same layer with multiple powers. And similarly, ground distribution, you have we definitely need to have the return plane, return current to pass through it. So we have to have the ground layer complete. It should not be a discontinued one. It should be a complete copper layer thing. For that, so as to signal can be used. It can be used as a return path for the circuit to complete. And in the case of SMT components or other FPGA or other components, we'll be having the ground pins inside the pins. So that has to be fanned out and it has to be placed very near to the device. So after placing, so this is the computer routing side of the PCB, and this is on top and bottom. Top side is the green color, the bottom is color. So it is the routing. The rubber band lines are used for completing this routing purpose. So as I discussed, based on the frequency, we need to place the component, and based on the digital or analog portion circuit, we need to define the component area, component size. So this is a general concept, the placing, how to place the component. That is, it has to be discontinued. It should not be a discontinued one at the ground side. And the power and ground traces has to be thicker in width to carry the perfect current. And as I discussed, the power decoupling capacitor should be very, very proximity to the power pad of the power pin of the IC. And why do we need ground and power planes actually? So this power and ground planes are definitely used for the return path of the circuit. So in case of, there will be two types of thing, there is low frequency boards and the high frequency boards. In case of high frequency boards, if you are placing if you are sending a signal that is from the IC, that is driver to the receiver, we are sending the signal. So the return path of the signal has to be continuous one. That is, it should not be a longer one. Like, so in case of low frequency, you can see the driver and receiver takes the return path of the driver current, driver to the receiver current has to be followed with the low resistance path. There is least resistance path. So least resistance path in the sense, so the top side is actually a copper layer, and the second side is a bottom layer, is a ground layer. There is full complete copper layer, and no discontinuity will be present in the ground layer. So it will take the least inductance path. But in the case of high frequency layer applications, it will take the least inductance path. Where if you have the discontinuity in the ground plane, that is the bottom layer, it will follow that particular impedance path, and it leads to the noise value. So because of this delay of the return path, it will create a noise in the circuit. That noise can translate into the signal integrity issues as well as the electromagnetic interference issues. So and placing the signal trace also very, very essential with the consideration of the current carrying capacity of the thing. And between the signals, you need to have the clear spacings without which we will get the crosstalk effects. So coupling effects will be happening. So finally, we'll clean up the silk screen for the legible presence and the aesthetic point of view. If your silk is, there is silk of the component, the designation of the component is filtered or it is merged with the outline of the component, so it has to be moved away from the thing for the legible visibility. And after things, so we need to have the assembly drawing for the assembling purpose, and this is the mask layer. And finally, we need to take the output of the from the EDA tool. So it will be, you can see it is a .gbr format, and this GBR format will consist of it's a text file which has the X and Y information of a particular trace or a component or whatever it may be. It will not have the complete intelligence of the component, and it has the size and shape information, that is the and location information. That's it. So using this file, the component manufacturers will process the production. And with this, I'll conclude the presentations. Next I'll go on to the demo portion, and I would like to hear if you have any doubts. I can answer just for 2 or 3 minutes. I hope you don't have doubts, or shall I proceed?
Yes, ma'am, you can proceed, ma'am.
Yes, so thank you, sir. So this is the Design Spark, which is an open source software by European country. Some RS component vendors, they have released this open source software tool. So which is I personally feel which is very equivalent to the high-end vendors like Cadence and other things. So I have worked on various high-end PCB tools. So based on those experience, I as a open source tool, it is very equivalent to those particular vendors. So for non-commercial purpose, you can very well use this open source tool, and you out of this you can generate the Gerber files, and you can design the PCB and generate the Gerber files. You can send it for the manufacturing also. So if you open this tool, it will be like this. So we need to create initially first file, new project. So this project as a normally every EDA tool, it will be the concept like we need to create a project. Under the project, we need to have the schematic design and the PCB design. So these two has to be come under the project. So initially we need to create a project. So here so this is the project I am going to create. So when you create this project, you will have the project window here. Here, some of the things are visible, and so the general settings are available here. From this thing, we need to create another new thing. So you need to create the schematic design. So here, when you create the schematic window, it will schematic design. You will have this schematic window. It will get open automatically. So you can see the grid are already set as default here, and we have to create the library first initially. So as I said here, go to the library manager, and it is we have 2-3 tabs here actually. So schematic symbols. So we say, as I already discussed, the logical representation are created in this schematic library, schematic symbol library. And the second one is the PCB symbol library. This is the actual part of the actual component part of the thing. So we need to give the clear dimensions in this library, this PCB symbol library or footprint library. And here we need to maintain the component like, so for example, if you take the LED, this is the car already created one. So this is actually a LED which is mapped. There is logical symbol is mapped with the physical symbol, and it is named as LED. So this the tool identifies this pin number 1 here is the pin number 1 here, and the pin number 2 is pin number 2 here. So each and every pad has a naming or numbering will be present inside this library symbol, which is automatically created while creating the symbol. So first we'll see how we can create the symbol using the library. So for example, I want to create a new library here. So I press new library tab, and I'm going to create a folder. And here demo schematic. So this is the demo. This is the library name. I am going to give the schematic for the schematic library as demo schematic library. So you can see nothing is created here. So the library name is demo schematic library. So here we need to create a library physical, logical symbol. You can use wizard. Here you can see whatever it may be. So you can, for example, if you want to create a resistor or resistor component, you can select the unit and precision in this window. So resistor has two terminals, right? So I am choosing this kind of pattern and pressing next. This information can be played around according to your need. And pins on left is 1, pins on right is 1. Distance between the things, if you want to take, for example, 5 mm or whatever it may be, if you want to take as per the actual thing, you can do it. Schematic. So you can see the resistor and the name of the resistor, one symbol is created here. So similarly, we can choose another component like, for example, rectangle, like this type of connector. You can choose pins on left, pins on right, pins on top side, like pins on. So sample has this many number of pins. So like that, you can select, and you can based on your number of pins in the component, you can create a component and add it to the new library. So similarly, for the PCB also, this is another this is a library name which is already in the in my system. So I am going to create a new library as demo PCB library. So I am saving it here. You can see now nothing is created, and we would like to create using wizard. So here the technology, you have to go through all this process one by one. So it will automatically, tool will automatically take you to the next process. So you can see the technology part. So technology, you can use the unit as mm and precision as 3 digits. And here you can type of components, like what there are various types of packages available in the component. So based on your requirement, you can choose the thing. So for the resistor we created, I am going to choose the dip component, dip kind of thing. So total number of pins 2 for the resistor, and you can see the pitch of thing. So there will not be a pitch because it is a 2 thing component, 2 terminal component, and the pad size and hole size you can play around. So hole size can be your depending upon your lead size of the resistor. So for example, if your lead size is 0.8 mm, I can use the 1 mm as a hole dia, and the pad size can be 1.5 mm for a 0.8 mm lead width. So these are all the things. If you want to take the dot, for example, if you are creating the IC, there will be a notch. There should be a notch. In such case, you can use these parameters. So the name here also I am giving the name as resistor. So this means this the resistor is created with the 2 terminals, and in the 2 terminals you can insert into the PCB. The resistor is created. So under the schematic symbol library, I have a resistor which is logical representation. Under the PCB symbol library, I have the resistor, the same name, which is a physical representation of a component. So I need to communicate, that tool need to communicate actually between this resistor and this resistor. Both are same, it should be same. But for that, the component tab plays a role for this communication. So here also I need to make a new library, new component library. And in this library, we need to give the connectivity of those 2 symbols. So here also I am using wizard. Next. So component name I give as resistor. And package is a through hole package, and reference we need to, since it is a resistor, you can start with R1, R2, R3, etc. So I reference designator, default reference designator is R. So number of components is, number of pins is 2. Number of pins is, we need to enter it as 2, and number of gate actually by default is 1. If you are using other digital components, you can use the gate concept. So you can see some other library has come. So I have to select the particular library. And next, similarly, we need to select the particular library. So here, this assignment of pins has to be happen. That is, pin 1 of the schematic symbol and the pin 1 of the PCB symbol should be assigned together. So this is how the tool understands that both those pins are same. So here I press assign 1 to 1. So here pin 2 and pin 2 of this PCB symbol are in the same mode. And I am saving this as in this particular library which is created. So you can see, so this resistor here, which I created here, and the resistor here, the physical component also it is displayed here. So likewise, whatever components which you have in the circuit has to be created initially. So these three tabs has to be used for this purpose. And some other, if you have the 3D file of the resistor, like 3D file, the step file of the resistor, if you have, you can add it to this particular, you can add the library, and it will be helpful for viewing the 3D view after the PCB design process. So I hope this is clear for the component creation of the library using the library manager. So similarly, we need to create all other components also. So currently, I will place a schematic editor. I mean, using this in this schematic editor, I am going to place the schematic symbol. There is a symbol which is created using the library. So this is the thing which is created by me for demo purpose. So just I am going to add this library. So you can see R1, R2, like this, it will get incremented. You will not have the redundant value here. Usually the designation of the component will be unique in nature. So similarly, so multiple components can be placed here, like similarly the resistor also will be placed according to your necessity. So I hope this is clear for you, creation of the library part. And we have the many other functionalities are present here. And using this color window, you can select this particular things if you want to change, and you can add various shapes. I can add components, which is I have shown already, and you can draw the schematic connections using these lines. You can add text also. And in the case of preferences, you have many preferences you can set prior to this designing the thing. And similarly, you have the design technology, which is a major concept, right? You have these many tabs. Text style can be set here as default. So so whenever you use in the editor, it will directly automatically call for with this particular style. And like that, connections also normal width also we can set using this particular tab. And net also there will be, if you have many other signals which is coming into this circuit, which will be directly displayed here. And similarly, you can group the net classes as signal, power, and ground. Based on your signal type, you can group the signals. And you can take the reports out of which we have the bill of materials report, dangling connections report. There is open connected report. So sometimes you might have forgotten the making the complete connection. So in that case, you will have the dangling connection. Sorry, and design status report also you will get, and generic netlist report and unconnected pins report. So various reports can be generated out of this tool. And once you complete everything, you can use this translate to PCB. It will automatically lead to the layout editor. So for just I'm going to insert few components which is already created for the demo purpose. So I am going to insert a timer. Next, I am going to insert. So you can see, so other components have it is already interconnected. So in the timer, you don't have the thing, so I cannot add it. So there is some problem in the connections issues. So I have some. I'll use Arduino for this. Arduino has many pins, digital, analog, and other pins. And I can use resistor. LED also doesn't have the thing, so I cannot insert it in it. Because the library library has not created for the LED physical and logical side. So that is why it is not coming into this window. So just I am making the connections and just randomly selected the paths, and I'm just making the connections between the things. So I just use this add schematic connections. So from this double click, I can just connect wherever I want to have. So if it is a ground and power pin, I can connect to the power D as it can be used as a decoupling capacitor. So I just randomly connect it for the demo purpose. So after, suppose if your circuit is completed like this, so after completing the circuit, you can take you can select whatever reports you wanted to have. So unconnected pins report I am just taking. So these many pins are not connected with other components. So since this Arduino has many pins, so I intentionally left the pins. So I can understand that I have not connected in it. So like similarly, if you want to generate the bill of material, you can just run the bill of material. You will have, so see, this is the bill of material I have used in my schematic editor. So one Arduino, two capacitor, two resistors. So like that, I can after checking all the connections with all the things, I can add the text like can increase the size. Increase the size based on your visibility. So similarly, all the things should be taken care in this schematic editor, and we have to select translate to PCB. So this is very important portion in the thing. So here, what I would like to select is the unit with 3 decimal precision. Next, I'm going to use since it is a simple board, I can use a single-sided board itself. Or else if you want to choose the up to 14 layer, you can choose using this software. And for the board shape, the next window is a board shape. So it will ask default shape. So if you want to select 100 by 100 board, so based on your need, you can change later very well. I am mentioning the arrange the outside the board of the component placement should be arranged outside the board. So it will arrange outside. So name, we can give the proper name for the PCB design. So some of the net class was not defined, so that is not a problem. So if you have more nets, you can define as signals and other things. Can group the signals like etc. So see, you can see the Arduino is very bigger than this board size. So I am just making the board little bigger. You can change, you can play around with the board size after placing the component. So you just pick and drag and place the component inside the board. So I want to have this Arduino in the center of the PCB. I'm just placing it and just picking the component. You can see the crisscross has happened. So I am just rotating the this particular component on more 90 degree, 180 degree, so that I don't need to cross this thing. And this rubber band line shows the connection which is derived from the schematic editor, right? And so to make this thing, I'll be handling this. So you can check the component properties by clicking the component, right click. So since this component is mirrored, it is created for the bottom side view. I am just mirroring it for, since it is a single layer board, I am just mirroring it to the particular component in the top layer, to use it in the top layer. And you can see various properties are available here, and the rate informations and other informations are available here. So what I do is I just pick the particular rubber band function and just drag it, or you can use this particular add track button and just do the routing. Similarly, you can complete all the routing, and one more thing you can here in this stage, you can, if your component placements are fixed, you can reduce the board size according to your thing. And here, if you want to have the copper core in it, so we can add a copper core area, and by clicking this core copper, it will ask for a net to process it, so that you will get this blue color, that is the green color indicates the copper port, where you will not get any short, you will get the clearance of the board between the sticks. So if you incorporate the ground plane in it, so you can make this copper as a ground copper, so that you will get the proper connectivity thing. So grounding helps us reduce the noise of the signal flow. So this concept can be used in the high-speed applications. So normally, right now I'll clear the copper. So normally, what low frequency boards will not. Uh, we don't need to pay the attention for this ground copper area, it's plain area. And here also you have the reports, the same bill of material reports, component height report, dangling trace report. So various reports can be generated out of it. And finally, after completing all the design work, you need to check the design rules for the spacing and completion and other manufacturing lines. So spacing in the sense it will check for the trace to trace distance between the thing. And for example, if you want to have only the trace to trace check, just checking, it will give the, if it is the less than the set value, it will provide the errors with location, corresponding locations. So that values are set in the design technology tab. Here you can see this under the spacing between the traces, it is set as 0.254. So based on your trace width, you can change the spacing values between the pads. So based on this matrix value, it will run against this design rule check value. So there are some online DRC is also available, and you can forward the design changes. Sometimes if you are doing the, you can place the component here itself. Actually, the process will be from the schematic. It is coming to this layout, and if you forget on in either component or some other things, you can very well insert in this layout, and it can be forwarded the design changes to the schematic side. So that is also possible. And similarly, cross-probing functionality is available. So, for example, if it is a big complex board, if you want to select the particular resistor in this layout editor, you can select the cross-probe functionality, and if you select this resistor R1, you can see this resistor R1 is highlighted. So this cross-probe functionality is also available from layout to schematic to layout. And similarly, the annotation between the component, annotation changes, there is changes between this layout and the schematic can be done easily. And you can optimize net, you can update the components. If you want to change the component, if you want to edit the component size or thing, if you are wrongly done, or if you have the revisions or other in any case of condition, you can very well do in the library and update in the layout editor as well as a schematic editor. So that for that, this update components tab is utilized. And you can optimize net, you can unroute the nets. So you can see, you can all the nets are unrouted here. And we have the design calculator. So this design calculator has the conversion and other RLC frequency calculations, heat sink calculations, and via track impedance calculations, trace width calculations, and other scientific calculations. So all other calculators are available. You can use this calculator for making this thing. And this edit side, you can have the properties. A property, if you are selecting the component and go to the properties, it will give you the complete information about the component as well as the net which is associated with this. And view, we have multiple views, multiple highlights and power planes and zoom and every and colors you can play around. And 3D also, we after completing the design, you can view it in the 3D. So since I don't have the Arduino 3D model, this taking default default value, default size of the Arduino portion. If you have the clear 3D of the Arduino, step file from SolidWorks or any other mechanical 3D software, we can directly import and you can view whether it is hitting the other component or other or not. So this is a very efficient tool for viewing the 3D purpose. And preference side, you'll before doing the design itself, you need to set the preference, like display preference, interaction preference, for cross probing preference. Cross probing in the sense you can find out the components very easily, and display speed and everything you can set as a preference. It is actually set for as a default. If you want to increase or decrease your you can do it. And grid size, you can play around. You can check. You can change the grid size. If you want to have the X and the Y as different, you can set that also very well. And coming to the units, design unit has to be. I prefer to use minimum. And if you want to have multiple units are available, and you can select either one of these. But keeping in mind the library and other part of the schematic, and everywhere you can select as as one unit. Otherwise, inch as common unit. And here the design technology, which for the spacing I have shown already, and the part styles you can select, and the text style you can select, and line styles and the trace styles, and layer information, this layer type, nets. So we have some six nets available. The net class. So all the nets are grouped under signal, and spacing matrix we can set. Rules other than the spacing rules, we can set in case of thermal, another drill spacing, another minimum track width. So against these rules, it will the tool will check the design rule information. So that for that the DRC, that is design rule check, is used. And the component you can place this as auto placement or manual placement, and auto routing is also available. So if you set the thing, it will automatically route as per your requirement, as per your rubber band line and spacing set already. And one more thing is here in the here you have the filter, like you can select, you can see, you take the layer, you can select the layer, you can switch off you can play around the layer silk screen thing. And if you want to go to the particular component, so here, so in this lesson we have used this particular component. So if you want to go to the particular component, you can go to the you can select the component. Here also you can add any components. So this window helps to assist while doing the complete design. So this colors in you can set for the particular top screen. You can, if you want to change the color of the yellow line, you can change. So whatever changes you want to have, you can. So I'm just switching on all the layers. And in the output side, we can very well export as a bitmap image or a metafile image and for the confirmation or for sharing the data, or and for sending it to the manufacturers, you can use this output manufacturing plots. Here you have a concept like you can use a PDF or Windows pen plot or Gerber. So here for sending the manufacturers, you can use this Gerber format, and layers if you want to set, if you want to remove the layer, particular layer, or whatever whatever you want to have, you can layer on and run. It will automatically create the text file which has the Gerber information, so it is design information. Of the layer. We have many help files available, and you can use this PCB design, design Spark as a PCB design thing, and you can download from the RS Components website. So this is a copyrights RS Components Limited and licenses. So now the project window, you can see the schematic file as well as the PCB file all together it has come. So if you want to add schematic pages, if it is a complex one, you can add the schematic like open, or you can rename, or you can duplicate. You can add it the schematic pages itself also. Similarly, for the PCB side, you can add the layers, but it is limited to the 14 number of layers. So that is a one of the limitations you can see. So normally in India, 2 to 4, 8 layer or 10 layer, 2 to 10 layer or the common manufacturers are available in India. So this is a design technology which is already shown you. And if you want, I hope you have the some idea about how the PCB design tool works and how the PCB design flow goes. So if you want to have any clarifications, or since each and individual area placement itself, it is a very long thing to do. So just confine myself for the particular portion. And so if you want to have elaborate, it can be taken later. And if you have any doubts specifically, I can clarify it. Participants.
Participants, if you have any doubts or queries, means you can ask.
So this process can be, this tool can be used in your project or mini project or your research projects. So for everything, you will be having some kind of PCB related touch, right? So this will be helpful. This tool will be helpful for designing your own PCBs. So this is a if you have any doubt, you can ask me later also. Sorry, all power electronics devices also can be implemented, or high speed application, or digital components also can be implemented in this tool, EDA tool. Normally, what does we do is after designing the complete high-speed PCB, it can be imported into the another simulator, which is for the signal integrity simulation and as well as the electromagnetics connected and radiated emission simulation, that is full wave simulator. With 3D solver, we can be used for measuring the conducted emission as well as the radiated emission, and because of that, the signal gets reflected. If there is any issues in the electromagnetic side, there will be a reflection in the source side, and the signal integrity will affect in the receiver side. So for that purpose, it will be measured, and if the simulation is not satisfied, it will be the layout, complete layout will be modified according to the simulation results, and so the iteration process. So that is the complete cycle of this PDF or the PCB design side.
Thank you, ma'am. I think there is no more queries from participants' sides, ma'am.
You are very clear with the
Yeah.
Somebody has reached. Then shall I stop sharing my screen, sir?
Yes, ma'am. If your side okay means you can stop sharing, ma'am. If there is no more means we can conclude, ma'am.
Yes, sir.
Let me conclude the session, ma'am.
Yes, sir.
Yes, ma'am. The roots of all goodness lie in the soil of appreciation. In this way, now I'd like to thank our today's resource person, Mrs. Y. Uma Maheshwari, for providing the wonderful practical session on the topic of PCB in the EDA tool. On behalf of organizing team and Komunadu College of Engineering and Technology, I'd like to thank you so much, ma'am.
Thank you so much for your invitation, and as much as possible, I have shared my experience with this given time. So thank you for the things. If you want to have the elaborative session, I can very well give in the whole complete thing, having the hands-on. It will be very useful the thing. So as of now, I have a satisfaction that I have just conveyed my whatever I have in my whatever I wanted to convey, and with this time. So thank you for this opportunity, sir. Thank you.
Thank you, ma'am. Thank you so much, ma'am. Dear participants, the day 9 session to attendance and the feedback link is posted in chat box. Kindly check it. Thank you all. Thank you, ma'am.